And share my screen, Today we're gonna go over the notes on PageRank 2 that I passed out last time on GitHub under the PageRank folder. Thank you. Any other papers that I'm missing that I need? Yeah, it's the notes2.pdf file if you're downloading it on the. Tell me I'm recording. Share the screen again. Okay. I think that's working. There we go. Okay, yeah, the PageRank 2 notes. We've finished what we're going to talk about for the PageRank 1 notes. There, I don't know, we did maybe like half to 2/3 of the problems in those notes. The other ones, the expectation is that you are able to work on those yourself. Have started working on them. You have those and the project to work on right now. The project again, due implementing your own PageRank, due this coming Sunday. And today and Wednesday, we're going to talk about the last of the math stuff about PageRank, and that'll be everything on the for the midterm exam. The midterm will have questions that are coming straight from the sort of problems that are in the PageRank notes here, but we'll talk exactly about the format and details of things on Wednesday. Today, we will just finish up these notes here. Any questions about anything about where we left off? Yes.
Are we going to have to turn in our notes one?
Question is, do you have to turn in any of these note packets? And the answer is no. The purpose of these notes packets is to give you practice. Well, I guess both to structure the lectures here and to give you practice problems to work on for the midterm, because the midterm is going to have problems just taken off of there. And again, in the midterm, you'll have, it'll be open notes, so you'll have access to your notes packets to complete them. So it would be good to make sure that, at least make sure that you know how to complete all those problems, if not actually complete them. But you're not going to be required to turn them in. Yes.
Next week.
So yeah, next Wednesday we'll talk about when the midterm exactly will be. It's going to be a take-home exam, so we'll get to negotiate when you all want to do that. I have no particular, yeah, I guess I don't care at all when we'll do it, except that starting Monday next week we're going to start new material that's not on the midterm, so I probably don't want to do too much of that before taking the midterm. Yeah. And the midterm, it'll be okay. So let's just talk about the midterm. Yeah, you'll have 48 hours to complete the midterm. I want to make sure that the midterm is after the due date for the programming assignment. Again, the programming assignment, I want you to be able to freely collaborate with anybody, however you want on it, whatever's going to be helpful for you to learn the material. And then the midterm, it's going to be open note, open book, but absolutely no collaboration at all. So that's why the midterm will have to be after Tuesday of next week. And I don't know, do people here generally prefer take-home test over a weekend, middle of the week, over a weekend? Here's some ooze. Yeah. No? That's your ideal, Sunday and Monday? Okay, well, yeah, so it'll be sometime after, we'll make a decision here Wednesday, sometime after at least 10 days from now. So not super soon, greater than 10 days, less than 20 days. Any questions material-wise on anything we've covered, not on the midterm mechanics? Okay, I think the last set of notes is, I don't know, there's a lot of like mathish stuff in the sense that there's a lot of memorization formulas, counterexamples, proofish things, but they're not really like interesting things from like a mathematical perspective. It's all that like trivial sort of stuff. today we'll talk about more interesting things and get into the actual like interesting parts about PageRank, and in particular, we'll tie it into or it'll start preparing us for the new material. So the first thing for us to talk about PageRank, I guess we've talked about all these like supporting things so far, but we haven't really talked about exactly I know any of the intuition stuff about PageRank yet. And the main idea for PageRank, when you're like thinking about when should I apply PageRank, the idea is that you have a graph somehow and you want to somehow find the most important nodes. And so there's a lot of ways that you might want to consider a node important. And one of those methods that you might want to use to consider whether a node is important is how many, so one measure of importance could be the number of links that you have coming into your web page, or the number of edges you have coming into your graph. And this is just basically restating this paragraph up here a little bit more succinctly. Links into a web page, or equivalently, it's equal to the number in degree of the node. And so the idea of this problem is to just sort of start thinking about like, how are these two measures maybe different from each other? And so if we have, say, a web page, just drawing a circle here as our web page, and all these other ones also web pages, nodes in our graph. If we have links like this, if you want to be a little bit more concrete, maybe this is like the New York Times right here, this node. These nodes out here are random people's blogs or tweets. So a lot of people talk about the New York Times. The New York Times rarely talks about other people's blogs. And so this is sort of obviously a very important graph, a very important node right here in this graph. And it both has a high in degree, and it turns out to have also a high PageRank. So the red, not part of the graph, just my notes about it. High in degree and high PageRank. In the PDF file, they talk about a number of different types of intuition for the PageRank. The one that I think is the most useful, or the easiest for me to, like, I guess, apply to a random graph that I see like this, is that random surfer model. The idea of that is if you're just like randomly thrown on one of these web pages, randomly thrown onto one of these nodes over here, and start following edges, where are you likely to end up? And for a super simple graph like this, it's obvious that you're just, no matter where you start following edges, you're going to get stuck on this node right here. So that's why it has a high PageRank, because you're going to get stuck here. And so this is going to be the only thing with actually any PageRank for this sort of graph. And it has a high in degree. For in degree, nothing else has any input edges. So here, in degree, PageRank highly correlated with each other. And it turns out that if you're like randomly generating graphs, the in degree and the PageRank are almost always going to be very similar this way. Turns out that's not always the case, though. That for a general graph, there's no actual necessary relationship between the in degree of a node and its PageRank. And so down here, I'm going to draw another picture. Very similar looking picture. All those arrows are supposed to point to this circle here. We'll add one other additional node down here like that. And now that node here still has the highest in degree. But that node over here has the highest PageRank. And again, with that random surfer model, if you're just like randomly starting on nodes in this graph, no matter where you start, you're always going to get funneled down to this node over here. And so that's why this node has the highest page rank of them all. Its in degree is only 1 though, so it's from an in degree perspective, it doesn't look quite as important as this node right here. You might think about like if, so maybe concrete web example again, if this node here, this middle one's the New York Times. New York Times probably not linking to random blogs, but maybe it's like linking to a senator's webpage or something. And so the senator's webpage is going to be very authoritative and have a high page rank. Any questions so far? Is this relatively intuitive? Yes.
That's like I was wondering like the highest degree is like how many
yeah, so the in degree of the node is the number of arrows pointing at the node. So here, the in degree for this middle node 4, I'll write them out in green. 4, 1, and then all these ones are zeros. And so I guess by in degree here, this one is it's second important, so it's not going to get totally ignored if we're just looking at the in degree. But it's still behind this highest in degree right here. Yeah.
Since you have to go from the node that's the highest degree, that's the only way to get to the highest page rank. Where do they have the similar page rank?
Yeah, the question is like how similar would these two page ranks actually be? And the answer is related to that alpha variable. We'll see that a little bit later on, but yeah, you could say they're similar, but this one's definitely going to be the higher of the page ranks because you're still going to be bounced under this sort of random surfer intuition. You're still going to be bounced over to this one more often. For these, actually the first 4 of these problems here are coming up with sort of example graphs satisfying certain properties about the highest or yeah, something about PageRank. Once you've completed your programming project, you could actually like compute the page ranks of these and see that this is going to be the highest. Question, any other questions so far? Just the main thing is this intuition about the random surfer model, following the links, following the edges to get to a spot, and that's going to give you your highest page rank. What this problem is actually asking for, it's sort of like, okay, this is one case scenario, but we want the worst case scenario. We want the situation like here, okay, they're kind of correlated to each other. Both of these have relatively high in degrees compared to all these things over here, and they're going to have higher page ranks. But what about the worst case scenario? The problem's actually saying that the bottom ranked node, according to in degree, is going to be the top ranked node, according to page rank. And so you can have them, like the best page rank actually be as far away from the best in degree, like arbitrarily far away. And the idea here is that if we added some more in degree nodes, in degrees to these over here, so I'm going to change this model again, draw another graph. And so let's do the same thing like this. Same one like that. So each time I'm just adding on new nodes and new arrows. Now the new nodes and arrows that I'm going to add are just to make sure that all of these have a somehow higher in degree than this one down here. And so we've got arrows going back and forth between them. So the in degree of each of these top nodes is 1. It's exactly equal to this. Let's add one more set of arrows going back and forth between them. And see if I can basically going to draw this as a complete graph on these 4 nodes. And I should have made them all just single or double-headed arrows like that to simplify things. But every one of these, if we connect every one of them to every other one, for example, so this is, I'll write it out just to make it clear what I'm trying to do here. Each node links to every other node in this little section right here. Then under this idea of the random surfer model, if I'm up here, I could stay up here bouncing around between these ones up here, and that would be great. But there's going to be some chance that I'll come down here outside of this little orange box. And if I ever come outside of this little orange box, then I'm never going back into it. If I'm ever leaving this orange box, I'm never going back into it. And so if I'm sitting around here long enough, eventually I'm just guaranteed to leave it. Bouncing around here, eventually I'll come out here, and once I'm out here, I can never get back in because there is no arrow coming back in. And then so once I'm at this node, I'm going to bounce down to this node. And so I'm still eventually, if I'm visiting random web pages, following random nodes long enough. Uh-oh. Got my stylus too close there. I'm going to eventually wind up at this node still 100% of the time. So now this one has the lowest in degree. Its in degree is 0. This one's in degree still 4. And all these ones up here will have an in degree of 3 because they're all connected to 3 other ones. And so it has the lowest in degree. Let me just write this out real quick. Lowest in degree, but the highest page rank. For that node right there. Yeah, hold on, question?
Yeah, I thought that sounds like there's one thing that comes to the last node that
Thank you, you're correct. Down here, I wrote a 0 next to this, but it has 1 arrow coming in, so it should still be a 1 like that one over there. A 1 right there. And so this final graph right here, and again, apologize for all that orange scribble in the middle, but a complete graph, everything's connected up here, is the change between these two graphs that causes the in degree up here to rise, but it doesn't actually change the page rank of those nodes at all. And again, so if you're thinking about like web pages on the internet and you want to somehow get your thing to the top of Google search, you might think about, okay, I'm just going to create like millions of random web pages all over the internet, have them linked to each other, and it'll be increase their page rank because they'll get so many links to each other. But without getting links back from these like really high authority, like New York Times or the Senator's webpage, back into your cluster of spam web pages, then you're never going to, these will never accumulate page rank. You'll always just be leaving there because there's no links going back in. One of the key sort of phrases that people use a lot is that the in degree measure, in degree is a local measure. You don't need to do any computation to know like what is the in degree of a node. It's just something that you have stored somewhere. And so it's local, only takes into account that one particular node, but the page rank is somehow global. The page rank of this node depends on like the actual internal structure of all the other nodes. And so it requires potentially these global things that consider the whole graph, potentially lots of computation. Any questions about that? The intuition behind the random surfer model for PageRank, the relationship between high, low, and degree in the PageRank. Let's see, how's anybody here think that you would have been able to come up with a graph like this on your own without talking about it at all? Okay, that's okay. How did we come up with this idea? Starting with a simpler graph and adding more things onto it one at a time. Again, the sort of simple graphs that you want to think about would be this sort of star shape where things are all pointing to one particular node. That was a great way to make high in degree and high page rank. So this is sometimes called a star shape. Everything's pointing together. I drew it as this sort of not star, but these are all on the outside. This one's on the inside, call it a star. Adding one coming out here, thinking about with this random surfer model, you're going to get stuck at these dangling nodes. So the dangling nodes, especially having high page rank. And then adding more edges up here, just trying to satisfy the property of the bottom ranked node according to in degree. Make this in degree smaller than these ones up here. Could have tried changing this in degree, but I can't really get smaller than 1, smaller than 0, so I made these ones bigger. The next 3 problems are all doing the same sort of thing. Either prove or give a counterexample to the following claims, something about PageRank. I wrote prove or give a counterexample, but all these happen to be counterexamples. So it says the node with the largest out degree can never have the highest page rank. So one of the things that we might think about, like thinking about these examples, well, this one here has a small out degree, and so it's maybe that's why it has the highest page rank, because it has a small out degree. It turns out though that the out degree is also not related necessarily to the page rank. I'm going to make another one of these star-shaped graphs. This time I'll actually draw it like a star. I've got 6 on the outside here. It doesn't matter how many are on the outside though. And if we draw a sort of star shape like that, then on any one of these nodes, no matter where I start, if I start on the outside, then I'm definitely going to this middle node. And then if I start on this middle node, I'm going to bounce back to one of these outside nodes. So half the time I'm going to be on this middle node, and half the time I'm going to be on one of these outside nodes. And so this middle node is going to have the highest page rank. And again, that's because no matter where I start on the outside, where you are on the outside, you're going to go to the middle node. Go to the middle node. And then the middle node you'll just leave. So half the time you'll be on the middle node, half the time you'll be on the outside. So that has the highest page rank. It also happens to have the highest in degree. All these other in degrees. So 1 in degree for all the outside nodes. Then the middle one, the in degree, is the total number of nodes we had on the outside. So I drew 6 of them. So the in degree equals 6 for that one. And in this case, every node, every edge is bidirectional. So we're going back to, or the in degree is going to be equal to the out degree. So the out degree is also 6. And so the out degree node has the highest page rank, which is a counterexample to this statement up here that the node with the largest out degree can never have the highest page rank. Any questions about that? Yes. Okay. Let's see. Feel like I need some feedback. So should I do another example or should we skip more examples? You feel like you can do examples on your own at this point or another example? Okay. Yeah, especially for things like, so the reason we're talking about these counterexamples is to get some intuition for what are the kinds of like graphs and situations where the page rank is a good measure of importance compared to these other measures. And so here, page rank, highest in degree, highest out degree, all be the same. Up here, it's different. And so depending on the graph structures, the different measures are either good or bad. Okay, so two nodes in a graph cannot have the same page rank value. So if we have 2 nodes in a graph, then let's see. My intuition when I'm thinking about trying to find counterexamples, I know it's always good to have like think about the smallest counterexamples that you can to something. And so I know in order for 2 nodes to have the same page rank value, I have to have at least 2 nodes in the graph. So let's start with a graph with 2 nodes. And then let's think about what are some of the possible, like, let's just think about all the different types of graphs that you might be able to have on 2 nodes. So this is one graph right here, the empty graph. Graph 1. Let's do another graph with just sort of a one directional arrow like that. And another graph 3, we'll make it a bidirectional arrow. And then let's try another graph 4. And let's do something like that, a link to itself, but not a link anywhere else. Graph 5, we'll do one link over like that. So just 6 graphs. We haven't talked about the page ranks of any of these particular nodes yet, but in order to think about counterexamples, we'll just start thinking about graphs, and then we'll think about what are their page rank properties of this graph, of these graphs. So here, this graph 1 in the top left, are these 2 nodes going to have the same or different page ranks? The same, because no matter like where I start in my random surfer model, I always just start off at a random node and then I randomly follow edges. There are no random edges to follow in this case, so each of these are going to have a like the probability that I'm on one of these nodes is going to be 1/2, and so that's their page rank, and they will have the same page rank. So I'll say this is the same page rank right here. And so this would by itself have been a counterexample. We could have been done, but let's keep talking about these other ones too, because we drew them out. And so this graph 2 right here, are these going to have the same or different page ranks? Different page ranks, because no matter where I start, which one of these nodes, I'm going to just end up over on this node over here. So this is different. And I'll write under the graph 1, counter example, and then not counter example. What about graph 3? Same page rank, different page rank. Okay, yeah, same. And so it's a counterexample, but I won't write it anymore. Graph 4, same or different page ranks? Yeah, so it'll be the same in this case, that no matter which of these two nodes you start off, if you're starting over here, you're going back to yourself following the edge. If you're starting over here, then you're just not going anywhere. There's no edge to follow. So same page rank. And then graph 5 over here, same or different? Different. We're always going to land on this rightmost node over here. Not a counterexample. What about graph 6 over here? Different. We'll always eventually land up on this rightmost node over here. So that one, those ones could have, any of those would have been fine. Examples of graphs that the nodes have the same page rank value. Any questions about that at all? Okay. So last one, let's see. I want to save at least one of these, so we'll not do this number 3 here and give you a chance to think about it a little bit and try to come up with examples, maybe as a hint. So again, so assume that all nodes in the graph have an in degree of 2 and an out degree of 2, then all nodes will have the same page rank. Draw a bunch of graphs that have in degree 2 and out degree 2 and try to come up with them. So yeah. Draw lots of graphs satisfying that condition. And so in particular that in degree equals the out degree equals 2, and just see which of them is going to have the same page ranks and which ones won't. Okay, yeah, from a, yes, question.
Good question. If you have like a cycle, like you do back to yourself, that kind of like, graph pointing towards you, like that kind of thing, or
So the question is, if we had something like that, is that going to be in degree or not in degree? And this here would have an in degree of 1 and an out degree of 1. Did that answer your question?
yes.
Okay, we're going to switch gears now. Start talking about the actual computations that are going into PageRank. We'll compute the runtime for computing the PageRank, and this will be useful for understanding the formulas that you're implementing in your programming project. So down here, number 2, runtimes. The idea, again, in your programming project, the main thing to do is to actually implement this equation 5.1 right here. It's equation 5.1 in the PDF, equation 1 in this in the notes packet. And for this part, we're just going to compute the runtime of this equation. If you recall that the source of this equation, where it comes from, 5.1, find me. There we go, it's this equation right here. And the idea is that we, in the very first equality right here, we have the x sup k, so the kth iteration of this x is the vector that we're computing. It's going to be our approximation to the k to the PageRank vector. The x or the k iteration is equal to the k minus 1 iteration times this p bar bar. Our goal is to compute the, I'll write it over here in the margins of this file. Our goal is to compute the top eigenvector. The top eigenvector satisfies this pi equals p bar bar. We'll put it on the left-hand side since it's over here. On the left-hand side, pi equals pi p bar bar. This is what just the top eigenvector of p bar bar by definition satisfies. And so our goal is to compute that. We'll do that by iteratively saying that this thing right here, this x at position k equals x at position k minus 1 times p bar bar. And if you substitute in and do some manipulation of the p bar bar formula, then you get this final equation right here. And the purpose for doing this substitution is so that you don't actually have to represent this p bar bar matrix anywhere. Again, p bar bar is dense because of that additional plus E transpose over in factor. This right here is just the matrix of all ones, E transpose. So it's going to be dense by definition. There can't be any zeros because we've added 1 to everything. But this P, the P matrix, is super sparse. And so we're computing this top eigenvector of this dense matrix by computing this formula on the sparse matrix, and that's going to make our runtimes fast. So this this next problem in the notes is going over what exactly is this runtime going to be. Before we get into that, what is this runtime? Any questions on this formula, where it comes from, what it's doing? Okay. So hopefully from the very first set of notes, we're experts at computing runtimes of matrix products at this point. Let's go through it. Here we have a vector-vector operation. The A vector is not something that I explicitly asked you to define and memorize on that quiz, but at least in my definition of P, it's included there. The A is equal to A sub I equals 1. Whenever we have one of those dangling nodes, I is dangling, and 0. I'll just say else. So whenever it's just an identification of which rows we're going to be modifying P into P bar with, so that we're adding the, making it stochastics, getting rid of those 0 rows. And so a vector-vector operation, we're taking an inner product, X transpose A inner product. So what's the, again, these vectors have dimension in. P is in by in, X is in, A also type in. So what's going to be the runtime of this vector dot product right here? That's right, Ovin, good job. So this is one of those BLAST level 1 operations, just 2 vectors, no matrix involved, and we get O of n. X transpose, vector transpose, another vector, dot product, BLAST level 1, O of n. The output of that's going to be a scalar. Let's say the dimension is going to be a scalar, so just a 1. And so then in green, all of this stuff all of that stuff, not including the V right here, but just all of this stuff here, after we do that dot product, all of that is a scalar. That the alpha is a scalar, that's that hyperparameter that we get to pick. And then here's the dot product, end result is a scalar. So that whole thing right there, scalar. We have a scalar times a vector. What's going to be the runtime of a scalar times a vector? Yeah, O of n, scalar times vector. It's another one of those BLAST level 1 operations of just manipulating vectors without matrices, no consideration of matrices. So scalar times a vector right here, O of n. So this whole, everything over here to the right side of this plus, the stuff in orange plus the stuff in green will be O of n. And again, we have two things that are O of n. Adding that together, we get O of 2n. Simplify, the whole thing just becomes O of n. So everything to the right of the plus, O of n. Any questions about why that runtime is O of n? The stuff in green and the stuff in orange? Does that make sense? Okay. I will interpret silence as a yes. So here we have a vector times a matrix. And this matrix here is sparse. So we're doing the sparse matrix multiplications. Everything else that we've done so far is dense. Really one of the tricks, yeah, I mean, this is not going to be, I don't think, too hard to implement in Python. The only thing that's sort of tricky is that you'll have to look up in PyTorch exactly what is how to use the sparse operations on the sparse matrices and make sure that you're doing this in a sparse mode instead of a dense mode. But the notes in or the comments in the problem just tell you exactly what function to look up to do that. So it shouldn't be hard. But when you have the sparse times a dense, that's going to be O of the number of non-zeros in that sparse matrix right here. And the notes from back before say that, and also the over here, it helpfully tells you that the runtime is in NZFP in the actual paper itself. Yes, question?
So on the part of like the sparse dense kind of thing, do we have to rearrange that like for the because in order to, the first one has to be sparse, right? So do we have to use like properties of matrices to rearrange?
Yeah. So here's the question is that PyTorch wants the thing on the left to be a sparse matrix and the thing on the right to be dense. And one of the other problems from the last 2 notes ago is how to use the transposes to do that rearrangement so that you can plug it into PyTorch.
Okay.
Yeah. Yeah, and so you have to be able to recognize that even though PyTorch has that like weird seeming built-in limitation, it's not actually a limitation at all. And so it's just sort of a notation thing that they happen to write it on the right-hand side here, but you can move it to the left just fine. Good question. Any other questions? Okay, so then the overall runtime of computing x to the k from x to the k minus 1 is going to be O of n plus n z of p. Just adding this thing and this thing together. Question is, can we simplify that? We sort of simplified up here of 2 O of n's, taking away one of those, so we just have O of n. Can we simplify this at all? In general, no. This is as simple as it gets. For the particular web graph in the paper, if you read through that paragraph, they're going to say that each row of P has O of 1 links, that web pages are just inherently finite sized, and so you can't have a web page that links to every other web page on the internet. Maybe the maximum's like, I don't know, a couple thousand. And so because of that, that would imply that NNZ of P is O of n. And so they simplify this to just be O of n, but I'll keep the more general. This is what I will keep. But they say O of n. because of this argument right here. Any questions about that? Okay. Power through. Number two, so if we're going to repeat this step capital K times, I've been very careful in this problem to differentiate between capital K's and lowercase k's. Capital K is somehow like I've decided in advance using my magical oracle that I'm going to run this algorithm capital K times. Then what's the overall runtime going to be? The lowercase k is like in your for loop, what you're iterating over. Here, the capital K, if we're going to do this capital K times, then the overall runtime is just K times this whole thing. So say K times N plus N Z P like that. And put a big O around the whole thing. So we're just repeating this thing up here, K times, so we multiply times K. In the real world, though, we don't actually know in advance like how many iterations we're going to need to use. Instead, we have this measurement right here that we want to keep going until our solution is somehow like really close to the final solution. And we know that our solution is really close to the final solution when our two solutions or our two iterates, the K and the K minus 1 iteration, get really, really close together. So this is that L2 norm right here. Again, the L2 norm, the normal Euclidean distance between these two vectors. And it's one of the most common ways of measuring how close together vectors are. When this goes to 0, so when epsilon over here goes to 0, then these two vectors are going to be the same thing. In the paper, they actually use tau for the letter epsilon. Tau for epsilon in the PDF. But for the rest of this course, whenever we see things like this, it will always be epsilon. Epsilon's a lot more common, so I put an epsilon here. Any questions about, does this make sense why this would be like a good stopping criterion? I want to set a certain like accuracy in advance, and then I'll just keep going until that accuracy is achieved, until my vectors are close together. Okay, so yeah, I want to format this in a nice way. So given in the text, they write this statement right here. Xk minus 1. So that's this residual over here on the left. I'm not going to put the 2 because the 2 is basically always the default. They say that's less than or equal to alpha to the k. And these all being lowercase k's here because they apply for every iteration, not just the very last one. And this alpha, again, is the subdominant eigenvector, or subdominant. Alphas are subdominant eigenvalue. And we know that it's strictly less than 1, not less than or equal to 1, but less than 1. That's why they did all those transformations on the P matrices, making sure that it was stochastic so that everything would be have eigenvalues less than 1, and then making sure that it was irreducible and primitive so that the subdominant eigenvalue would be strictly less than 1. There's going to be strictly less than 1. So when we raise something strictly less than 1 to the k power, it's going to get smaller and smaller and smaller exponentially. And so these two things are going to get smaller and smaller and smaller by the construction of the P matrix. Our goal is to ensure, and let me also again say that this part over here to the left is just given to us. And they go through some fancy linear algebra proofs that argue that more concretely. We don't need to worry about that so much, as we'll just take this as given. And what we want to do is if we set this thing over here, set that to be less than or equal to epsilon, that being an epsilon, then solve for k. If we do this thing over here, solve for k, then we'll have some number k that guarantees us that we will be less than or equal to epsilon. So this one over here is what the problem is asking for. That's our goal. Showing that this thing in red, the residual, is less than or equal to epsilon. Doing that, alpha to the k less than or equal to epsilon, taking the log of both sides, k log alpha less than or equal to epsilon, and then, oops, less than or equal to the log of epsilon, and then k less than or equal to log epsilon over the log alpha, like that. With that little relationship, then we can plug back into our formula from above. So this here is our formula for k log epsilon over alpha. That's the actual answer to computing the formula for the number of iterations k required to achieve a residual less than epsilon. Plugging that into our previous one, we'll get that our final runtime O of log epsilon over the log of alpha times n plus n z of p, like that. And that right there is going to be the runtime of the PageRank algorithm that you're implementing. So as you can see, a couple just high-level things to note. This is more complicated than maybe your typical data structures runtime of like n squared, log n, things like that. We got logarithms going on. We got things down in the bottom of a denominator over here. And so it's important that you're able to do the like going back to the actual definitions of our asymptotic notation when you're working with things like this in order to understand what's bigger than other formulas. And another good thing to do is just to think about, like, if we start plugging in numbers, then how are things going to like relate to each other? Does it make sense at all? So let's think about our epsilon. If we want something to be more accurate, then how is that going to actually, like, how does this actually affect things? If we have, say, epsilon equals 10 to the negative third. That's a common, relatively large residual, but still good enough that you get good accuracy. So that's a common value to use for epsilon. And if you take the log of that, log of 10 to the negative third, what are we going to get? -3. So let's do one more down here. Epsilon equals 10 to the -6, and then a log of 10 to the -6. What's that going to be equal to? -6. And so the thing up top here is going to be getting more and more negative as my runtimes, or as my accuracies are getting more and more precise. So this is a more precise accuracy right here. 10 to the -6 is a more precise accuracy than 10 to the -3. And my runtime now seems like maybe it's getting more and more negative. Have we made some sort of major mistake? And the answer is no, that it turns out that this log down here is actually also going to be negative log of alpha. Alpha is constrained to be between 0 and 1, so we're going to get negative values right here. And the negative from the log of alpha will cancel out with this negative right here. So because both the epsilon and the alpha constrained to be less than 1, both of these logs are going to be negative. Both of those negatives will cancel out. Log of epsilon, log of alpha, both negative. And they both cancel out. So here, this negative right here is not actually impacting the, we're not getting more and more negative here, we're getting more and more positive. And so by making my residual go to 10 to the negative 6, it's going to take roughly-ish twice as long, going from 3 to 6. Plugging in 10 to the negative 3 right here versus 10 to the negative 6. 10 to the negative 6 will give you twice as large of a value. Any questions about that? And one of the things that you should be able to also think about, reason through for the midterm is like, okay, is this going to be faster if alpha is closer to 0 or if alpha is closer to 1? Which of those will be faster? Yeah, so I didn't write this out as an actual question or didn't print it as a question, so I'll write it right here. Which is faster, alpha close to 0 or alpha close to 1? And I heard somebody was alpha close to 0.
Yeah.
Why?
Because the log graph approaches negative infinity as x approaches 0. So that's a negative infinity denominator, which will be more at one time. Whereas it's a very small negative fraction if you approach, like it approaches 0 as x approaches 1, which is going to be a very small fraction and the denominator.
Yep, yeah, all that is exactly right. As alpha, so I'll just repeat it now. As alpha goes to 0 down here, alpha goes to 0, log alpha will go to negative infinity. Those are alphas. That's an alpha, that's an infinity. You get an infinity in the denominator down here, and it's going to, whatever your runtime is, however many rows you have and columns, whatever accuracy you want, you're dividing by infinity, so you're going to get an instant runtime. And then the opposite is true as you the log of, as alpha goes to 1, the log of alpha is going to go to 0. You're dividing by 0 down here, so that's going to blow up to infinity. It's going to take a really, really long time. So as you're working on any sort of PageRank problem, but in the project in particular, I'm asking you at different points to use different values of epsilon and use different values of alpha, and you will see that actually play out in practice in terms of the runtime of your code. That I guess it's in some sense should be intuitive that you want a more accurate result. It's going to take longer. So I think the log epsilon on top, relatively intuitive. The log alpha on the bottom, much less intuitive though. But you'll actually see that play out. Questions on that? Okay. There's a couple of implementation detail notes down here in this part 3. I want to make sure we talk about that because that'll be important for when you're thinking about your project implementation. And I'm going to jump over to problem 7 over here. We only have a few minutes left, so I'm going to not do this formally, just informally. But again, x k defined by equation 5.1, x k minus 1 times p bar bar. It's just the definition from equation 5.1. And so we know that the eigenvalue of p bar bar, the largest eigenvalue. What's the largest eigenvalue of p bar bar? Is p bar bar a stochastic matrix or a non-stochastic matrix? It's stochastic, and one of the properties of the stochastic matrices is that their largest eigenvalue is always equal to 1. So the largest eigenvalue of p bar bar is equal to 1. And so we know that this is never going to make the norm, the magnitude of this vector larger, because when we do the multiplication, the biggest that it can stretch something is by 1. And that's not larger. It's going to be the same. But the subdominant eigenvalue, what's the subdominant eigenvalue of p bar bar? Alpha. So this hyperparameter alpha, the reason we constructed p bar bar the way it is that it makes the next eigenvalue be alpha, and this is strictly less than 1. And so any x vector, unless it happens to be exactly equal to pi, unless it is exactly pi, which is the largest, or is the eigenvector corresponding to this largest eigenvalue, any x vector is going to be shrunk by this factor of alpha. And so xk is always going to be, or the L2 norm of that is always going to be less than that alpha factor, doing this p bar bar right here of the x k minus 1. So the fact that we have eigenvalues that are less than 1 is causing this shrinkage to happen and causing this to be a strict inequality and not a less than or equal sign. And so because of that, in order to make your code actually work, you're going to want to say at some point that x sub k, renormalize things, equals x k divided by the L1 norm of xk, and this will ensure that xk is always a probability vector. Doing this variable assignment right here will renormalize xk so that it is a probability vector, so that it'll sum to 1. And then even as things shrink, you'll blow it back up using this, so it all stays the same. Yeah. End of class for today. If anybody has any other questions about anything, happy to stick around and answer them. Otherwise, hope you have a good rest of the day. Make sure you're getting started on the programming project, working on these other problems, and I'll see you all on Wednesday.
Thank you.